This is the third video from section 4-4 of the counting rules, permutations and combinations. All right, we're going to start out with an example. Example 24. How many ways can 8 students fill 8 seats in an auditorium row? This example, more than most examples in this class, causes a lot of people, it counters their intuition. I know this is one that the first time I looked at this, when I took this class, I was thinking, oh, probably 64 ways. But 8 students, 8 seats, ought to be about 64. Well, as we're going to see in a second, my intuition was way off. You could attack this with the boxes that we saw in the earlier video. We have 8 boxes to correspond to the 8 seats. For the first box, we have 8 possibilities. Any of the 8 children could sit there. For the second box, there are 7. Third box, 6. Fourth box, 5, and so on through that. When we multiply this chain together from 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, the answer is 40,320, which is considerably north of 64. Similar question to this would be if you said, okay, I had 8 songs on a portable music player and I had a shuffle. How many different sequences could those 8 songs play in? 40,320. So don't worry if your intuition kind of gave you a lower number too. All right, now with that in mind, we're going to define permutation and combination. A permutation is an arrangement of objects in a specific order. A combination is a selection of objects without regard to order. So with combination, we're just dividing the set up. All right, now, permutation rule 1. An arrangement of R objects selected from n possibilities. So you'll see the notation here, capital P for permutation. To the left, there's a subscript, the n. That is the number of objects, or the pool. R is how many of those objects we're selecting. All right, so the formula to calculate this is n factorial in the numerator, n minus r in parentheses factorial in the denominator. Now, if we would look at example 24, actually we'll do example 25 with the formula. Okay, a foreign company wants to create a list of their top 3 U.S. states for expansion. How many different lists are possible? Okay, so in this case, we're going to assume that you can't duplicate between the 3. We want 3 different U.S. states. So you could attack this with the boxes and the fundamental counting rule and say, okay, there's 50 possibilities for the first choice, 49 possibilities for the second choice, 48 possibilities for the third choice. Alternatively, you could recognize, hey, this is a permutation problem. I could use the permutation formula. The pool size, there's 50 states to choose from, and I'm going to use 3 of them. So I plug into the formula. Numerator is the pool 50 factorial. Denominator, the pool minus how many I'm using, 50 minus 3 factorial. Now that's in parentheses, so I need to do subtraction first. So I'm left with 50 factorial over 47 factorial. Now this is where that rule I had showed you in the factorial video comes in handy. Everything from 47 on down cancels out in this case, leaving us with just 50 times 49 times 48. And when you do that multiplication, 117,600. Now, as I said a couple minutes ago, you definitely could have used the boxes on this. And that's the nice thing with the permutation problems. You have a choice. You can do the boxes or you can do the permutation formula, whichever makes more sense to you. All right, example 26. Draw 4 cards, one at a time, without replacement. How many sequences are possible? All right, in this case, again, you could use the boxes, but we're going to use the formula here and show, okay, it's a permutation problem because the order matters. In textbook problems, oftentimes you'll see the word sequences, and that typically is a tip-off that the order does, in fact, matter. So our pool size is 52, because there's 52 cards in the deck. We're going to use 4 of them. Plug that into the formula, 52 factorial in the numerator, 52 minus 4 factorial in the denominator. Do the subtraction. We have 52 factorial over 48 factorial. Everything from 48 on down cancels out, leaves us with 52 times 51 times 50 times 49, which is 6,497,400. All right, now, flip side of that is the combination rule. Number of combinations of our objects selected from n objects. Now, the first thing you'll see is the notation is the same. Instead of a P with the subscripts N and R, we have a C. Permutation combination matches up. The formula is similar. Numerators are the same, still n factorial. Denominator, we've got the n minus r factorial, but we also have this additional term down here, or additional factor, r factorial. Now, what that extra r factorial is doing is that is getting rid of the sequences that are only different in the order. So we have the same objects, just in a different order. So that's what this r factorial is doing, is we're dividing by that, and that's helping us to get rid of those. All right, example 27. 2 employees from within a department of 10 employees will be chosen to attend a user group for the software they use. How many ways may the 2 employees be selected? Okay, now the first thing to recognize is you have to ask yourself, is this a permutation problem or a combination problem? And in this case, it's a combination problem because order doesn't matter. You're either going or you're staying home. So it's not a matter of you're the first one going or the second one going or the 7th one staying home. You're either going or you're staying home. So all we're doing is dividing the set into 2 people who go and 8 people who stay. So it's a combination problem. So, combination problem, the pool size is 10. We're choosing 2. Numerator 10 factorial. Denominator 10 minus 2 factorial times 2 factorial. Do the subtraction inside the parentheses. Now, what I generally do is I apply that factorial rule with the larger of the 2 numbers in the denominator. So 10 factorial over 8 factorial is going to leave me with just 10 times 9 in the numerator. And then I need to not lose track of this 2 factorial. That's 2 times 1. So the numerator is 10 times 9 is 90. Denominator 2 times 1 is 2. 90 divided by 2, 45. So there are 45 ways we can select 2 people to go to the user group. Couple more examples just to demonstrate this. Example 28. Golfer owns 20 different golf clubs. Rules specify a golfer may not carry more than 14 clubs in their bag for a round. How many different ways may the golfer choose to meet this requirement, assuming they carry 14? Believe it or not, that assumption makes this problem simpler. The problem's far more complicated if they were allowed to carry less than 14. We'd have to account for what if they carry 13, what if they carry 12, what if they carry 11. All right, so 28. Now, this is another combination problem. We don't have to worry, it's not that this is the 3rd club in the bag or the 11th club in the bag. It's the club's either in the bag or it's not. It's in the trunk or the hotel room or wherever. So it's a combination problem. Pool size is 20. We're choosing 14. Numerator is 20 factorial. Denominator, 20 minus 14 factorial times 14 factorial. So we have 6 factorial times 14 factorial. I cancel out between the 20 and the 14, which gives me 20 through 15 down in the numerator. And I still have the 6 factorial in the denominator. And when I go through and do all the multiplication and division, I end up with 38,760 different ways I can meet that requirement. All right. 2 more short examples. Example 29 is meant to show the difference between permutations and combinations. If all tickets are held by different people, how many different winner lists are possible? So 2 raffles here. Raffle 1, raffles held with 10 tickets. First ticket drawn wins 1,000. Second ticket drawn wins 500. Third ticket drawn wins 300. Second raffle is held also 10 tickets. First ticket drawn wins 600. Second ticket 600. Third ticket 600. So both raffles give out $1,800. The difference is, in the second one, I don't care which order I'm picked in. If I'm chosen 3rd, I can wait till 3rd to get my $600. In the first one, I care which order I'm chosen in. If I'm 1st, I get 1,000. If I'm 3rd, I get 300. So raffle 1 is a permutation problem. Raffle 2 is a combination problem. Both cases, the pool is 10. We're choosing 3. And you'll see you work through the math here. Again, raffle 1 you could do with the boxes. You're left with 10 times 9 times 8 is 720. In raffle 2, you've still got that same numerator, 10 times 9 times 8, but we need to get rid of the duplicate winners lists where all it differs is the order, and that's the 3 factorial, 3 times 2 times 1, so 720 divided by 6 is 120. All right, and finally, example 30. Track coach has 9 runners available for the distance medley relay. Each of the 4 legs runs a different distance. How many possible relay times may the coach choose from? All right, now this is one, I consider this to be clearly a permutation problem because each runner runs a different distance. So we have 9 runners to choose from. We're going to choose 4 of them. It's a permutation problem. Again, could use the boxes. 9 people for the first leg, 8 people for the second, 7 for the third, 6 for the fourth, 3,024 possible different relay legs. If you had assumed it was a combination problem and ran through it like that, you would come up with only 126.